Cool. All right. Hi, guys. Well, welcome to Geometric Satake Day 5, the final day of Geometric Satake. So that's pretty intense. So I guess I kind of want to just start by picking up where we left up yesterday. There were a couple of things that I intended to say that I didn't get to, so I'll just kind of say them now. So firstly, we sort of, at the end yesterday, we ended with this theorem that we can basically decompose cohomology into these weight functors. So something like this. And in particular, this is super, like it's not just a way of showing that cohomology is exact and faithful, though that's certainly a very important reason. It also sort of adds more data to this functor. So in particular, we have this map from the Satake category down to vect K, which is cohomology. But now it sort of factors this map as a map into vector spaces which are graded by co-weights, right? So we can just sort of take the direct sum of the weight functors, and now we get a map like this.
Is there supposed to be a direct sum in the line, the first line, the theorem?
Yes, there's definitely supposed to be a direct sum, and the direct sum is over all co-weights, even though I haven't been writing that. But yeah, and this is sort of not just like a fancy thing that we're allowed to say. This thing is isomorphic to reps of the dual torus, right? Because representations of the torus are just weight, so co-weights are representations of the dual torus. So already sort of we want to be thinking of the Satake category as something that's hopefully going to be a representation of G dual, and this is actually going to be the forgetful map down to representations of T dual, it's going to turn out. So I think like Aaron asked yesterday, like why we're just kind of going down to vector spaces and forgetting the Z grading on cohomology. And I said like there's more structure, but we'll get to it eventually. So this is like the more structure that I was referring to. So this will sort of further factor obviously through the Z grading, but this is kind of the grading that we get on cohomology by doing this whole thing. And it'll turn out to have plenty of geometric significance. So the last thing that what's up?
Also, yeah, so maybe so last time, sorry, so I'm just trying to think about how does the grading by the co-roots correlate to the grading by like the Z grading. Is that because we implicitly pick that role and that's the
yeah, it's because each of these weight functors was like cohomology in a certain degree.
And that's connected by role, right? It's just
yeah, like each of these will be like F mu will go into like the row 2 mu cohomology.
Okay.
Yeah.
Okay. Thank you. Yeah.
But yeah, I mean the Z grading itself isn't actually important. This is the grading that matters. But yeah. But anyway, so the other thing that we sort of have left over for tomorrow from yesterday is to show that cohomology is faithful. So this is not going to be super difficult, but we'll just go ahead and prove it. So we know that usually faithful means that we don't send any non-zero map to 0. So we have an injection on the level of Hom sets. But since we know that cohomology is an exact functor, that's the same as showing that no objects are sent to 0. So we just have to show no objects go to 0. So how are we going to do this? Well, let's pick some F in the Satake category. So we can pick some dominant co-weight such that sort of its corresponding Schubert cell is open in the support of F. There's always going to be one, which is, or at least one, which is open in the support of F. And then sort of by perversity conditions, the restriction to that Schubert cell is just going to be the constant sheaf on some vector space with an appropriate shift in dimension. So M is just a K vector space, and M with a line under it's like the constant sheaf on that vector space. So then just sort of by the closure relations on these two stratifications that we've been talking about, we're going to get that S negative lambda intersecting the supportive F is just going to be S negative lambda intersect GR lambda. and that's just going to be L of negative lambda. So if we try taking sort of the negative lambda weight functor on F, I probably shouldn't have called it F, but I did already. That's just going to be, as we discussed yesterday, the negative 2-row lambda compactly supported cohomology of F restricted to S negative lambda, but by what we have above, that's just, well, F restricted to S negative lambda is literally just F restricted to a point, to L negative lambda. And now we know that that's just going to give us sort of that cohomology group of this, well, it's just going to give us M, right? Because it's just a point, and we know that on GR lambda, we have this constant sheaf with this vector space in that specific cohomology group. So we just get M, and M is not equal to 0. So we have that at least one of the weight functors is always going to send you to something non-zero, and thus cohomology is faithful. Great. So that's kind of the end of yesterday's talk, which I envisioned. But
Alberto, can you say again why we know there's such a lambda where the support is open?
yeah, so I mean, basically it just kind of comes from the fact that we can think of like sheaves on the affine Grassmannian as sort of sheaves on these like Schubert varieties. So there's going to be kind of some like maximal Schubert variety that it's, or some like minimal Schubert variety that it's supported, that the support is contained in, and then that corresponding Schubert cell should be open in the support. I think that should more or less work. I mean, intuitively, if there was just the way kind of since it's a stratification, I think generally speaking, if you have a sheaf that's constructed with respect to some stratification, there's always a stratum that's open on its support.
Oh, right. I forgot constructibility. Thank you.
Sure. Yeah. No, that's fair. Yeah.
Wait, Alberto, what are you saying? Open on the support? I'm not quite sure what you mean by that.
So F is something in the Satake category, so it's a constructible, in particular perverse sheaf on the affine Grassmannian.
Right.
And then we just picked some Schubert cell, which is going to be open in that support.
Oh, okay. But didn't you just say that there's some Schubert cell that contains the support of F? Is that not the same Schubert cells we're talking about here? Or
so there's going to be some like Schubert variety which contains the support of F. That's like the closure of the Schubert cells. And I was saying that there should be some minimal one that contains some minimal Schubert variety which contains it, and then the Schubert cell corresponding to that one should be open in the support. So that was just kind of like, I might be wrong about something there. That's just sort of what seemed like the answer to me. But generally speaking, I think if you have a constructible sheaf on like a stratified space, there should always be some stratum which is open on its support. Does that seem like a reasonable thing to think?
I guess it's the phraseology "open on the support" that kind of confuses me.
Like
So
it's an open subset of the support. It's an open subset of the support.
I see. So it's both contained in the support and open, is what you mean?
No. It's not. Yeah, it's contained in the support and it's open in the support. Yeah.
Okay.
It seems like that might require some conditions on stratifying poset, like maybe Artinianness or something. I don't have anything more to say, but just as a general comment.
Yeah, I could definitely see that. I could definitely see that being true. Yeah, I mean, I could see that being true in general. I mean, usually, like a lot of times with this stuff, you're just dealing with finite stratifications. And in the affine Grassmannian, it's obviously infinite, but it's sort of this co-limit of finite things. So you can always sort of just pick a big enough Schubert variety and say that's supported on that, and then kind of appeal to finite stuff. Is there, how much skepticism are we feeling about this?
I wouldn't belabor the point.
All right. Well,
I just want to clarify what you were saying because I wasn't
yeah,
sure
exactly. Well,
what the actual words meant.
yeah, what I was saying is that maybe is open, maybe definitely in would be a good word there. But yeah, I was saying that there's a Schubert cell that's contained the support and open in the support. Cool, great. So anyway, so what's sort of the goal for today? So the goal for today, well, I'll just say, so now we know that cohomology is exact and faithful. So actually the only thing that we have left to show to know it's a fiber functor is that it's symmetric monoidal. So obviously in order to do that, we're going to have to define a convolution structure. So define a convolution on the Satake category. Then we're going to want to show its symmetric monoidal, and not just symmetric monoidal, but that H sort of is, I'll just write SM, that H is symmetric monoidal, and then we can use Tanaka to get, at that point we can finally use Tanaka to get that Satake is isomorphic to the reps of some group G tilde, so we'll have to show that G tilde is actually isomorphic to G dual, and that's sort of what we're going to do today. So, so it's mostly going to be a day about convolution. Great. Okay. So having said that, let's sort of begin. So the first way that we're going to define convolution is going to be completely analogous to sort of the way that Saad defined convolution. It's going to be sort of the classical convolution product. But let's kind of remember how this works. So we have GRG cross GRG, and then we have a map from GK cross GRG, yeah, find Grassmannian down to that, which is just the quotient on the first factor. We also then get a map to GK, so sort of cross over GO with GRG. So this is sort of the diagonal quotient. So we have a diagonal action of GO sort of by multiplying on the right the first factor by something, and then by the inverse of that on the left on the second factor. So we can quotient out by that diagonal action. We're often just going to refer to this as GRG sort of like this. It's just going to turn out to kind of be a useful notation. And then we have a map down to GRG. And maybe we even kind of want to be a little bit more specific here and say, so this looks like an element of GK in a coset. We'll just send this straight down to just taking the cosets of both of them. We'll send this to sort of, that's now like a representative of that quotiented out by the diagonal action. And then this map is just going to be multiplying G and H. And that's not going to depend on what coset representative we chose, because the two things which are inverses will just cancel. So we definitely have maps at the level of spaces. Now let's sort of upgrade these to maps at the level of sheaves. So I'm going to kind of write things as constructible sheaves rather than as perverse sheaves, because at least for the time being, we don't know that all these maps are going to map perverse sheaves to perverse sheaves. In general, they don't. In this case, they do. So yeah, so we have maps on these derived categories of constructible sheaves.
A quick question, Alberto.
Yeah.
When you're using this notation that you just underlined for the cosets, would it be like technically G times G of O? Or what does this mean?
Did I underline? Are you talking about over here?
Yeah, just G times O, H times O. What is that?
So basically, the idea is sort of that this space is like the space on the left of it quotiented out by something. So I'm just kind of writing like a representative of that quotient. So like GHO gets sent to like GHO, like that coset of this by the diagonal action. I couldn't really think of like a better way to write it. I don't know. In my mind, it was sort of analogous.
No, but he's asking, should that O be a GO? Because the Grassmannian is
Oh,
GK mod
yeah,
GO.
these O's should all be GOs. Okay, I'm not going to replace each one, but there's 1, 2, 3.
That's a fine
4.
shorthand. I just wanted to make sure I understood.
Yeah, all 5 of the ones in that row should have been GOs. So yeah.
Also,
it's good.
Alberto, I think I missed, what does this notation mean where you write like GK product GRG, but then the GO is a superscript, or?
Yeah, so the superscript sort of thing means we're quotienting out by the diagonal action. So if we have a Cartesian product and then we have some group that can act sort of on the left, on the right to the thing on the left, and on the left to the thing on the right, then there's a diagonal action sort of multiplying by x on one side and x inverse on the other side. We're quotienting out by that. But we're sort of going to get other convolution diagrams as we go, and sometimes it's not going to be as nice. So we're usually just going to use the sort of like GRG cross tilde notation. But anyway, so we get this sort of map on just the derived category of constructible sheaves, and our goal is sort of to go all the way from the left to the right, and we can see that our issue is sort of this Q pullback map that goes in the wrong direction. So we're just going to sort of note that the map Q is a GO torsor. So sort of Q pullback is so Q pullback, I'll just write, is an isomorphism onto sheaves which are GO equivariant with respect to the diagonal action of GO. So this is very much analogous to what Saad was talking about on Tuesday. So in particular, the things that we get when we pull back from using P, well, we're going to start with perverse sheaves which are equivariant on both factors. So when we pull one of those back, we're going to get something that has the necessary equivariance, and then we can always find something that Q would have pulled back to that because of this. So in particular, now we're kind of going to actually define the convolution product. So for F and G in the Satake category, we can take the box product of them, and that's definitely going to be an element of this first thing. I'm not going to sort of write out the equivariances throughout, but it's going to be equivariant on both factors. And then let F sort of box product tilde G be the unique element of this guy such that sort of the Q pullback of this tilde box product is equal to the P pullback of this. So this is kind of our equivalent of like push of going to the left. And then we can just define the convolution to be the push forward on M of this sort of tilde box product. And that's going to give us our convolution product. So the issue right now is that our convolution product is only defined at the level of constructible sheaves. So it's going to turn out that if you take in two perverse GO equivariant sheaves, you do get one out at the end. And that's basically going to follow from keeping track of dimensions throughout. In particular, what's very relevant here, so let me just kind of write this as a fact for now. If F and G are an element of the Satake category, then the convolution product will too. And by that, I basically mean it's a perverse sheaf. So I'll just write sort of main idea, because I don't think it's super illuminating, but the main idea is that M is a stratified semi-simple map. So for those who which that means something, semi-small map, sorry. It basically is a condition on like the dimensions of the pre-images of strata of certain dimensions. And essentially just those conditions are going to be exactly the right thing, that it's going to preserve perversity, because perversity is basically also sort of a condition on the ranks of things in certain dimensions. And we're going to know it's a stratified semi-simple map by going through sort of the details of all the dimension counts we found yesterday. So I'm not going to do that, but it takes a little bit of work, but it's not super illuminating. And we sort of get that we actually have a map from Satake cross Satake to Satake. Furthermore,
Sorry, could I just ask briefly, you said something about equivariance of F and G separately or something like that? Could you elaborate on that?
Yeah, sure.
So that it lands in the GK equivariant.
Yeah, so there's a lot of equivariances. Yeah, great. So there's a lot of equivariances sort of around here, which I haven't fully talked about. But when we start with something right here, when we start with like F box product G, it's going to be sort of GO cross GO equivariant. It's going to be GO equivariant with respect to the left action on the first factor and also with respect to the left action on the second factor, just because F and G are both elements of the Satake category. And then when we pull back with respect to P, we're still going to get two equivariances. We're still going to have sort of an equivariance with respect to left action, but then the other equivariance is sort of going to become an equivariance with respect to diagonal action. And then because we get something that's equivariant with respect to diagonal action, we know that there's actually going to be something in the third sort of space which pulls back to that guy. And the left equivariance is just going to work its way down and work its way down through M all the way to the end. And we're going to get that we end up with something that's GO equivariant, which is what we want, because we want to start with two sort of like F and G sort of by definition are both elements of like, you know, perverse GO equivariant sheaves on GK mod GO.
Oh, I'm sorry. That's the entire thing I was forgetting, was that equivariance right there.
Oh yeah, that's fair. Yeah, I mean that's my bad.
Great.
I probably should have. But yeah,
there's a lot. That's fine.
Yeah, there's a lot, and there's going to be more, unfortunately. But yeah, that's where the two equivariances sort of come from, and then one of them makes Q sort of work out, and the other one persists all the way until the end, and make sure we end up with something equivariant. Okay, great. So
Alberto?
Yeah.
Up above you write like Q is a geotorsor. Do you mean like geo intertwiner or something like that?
I think I mean geotorsor. I mean Q is a free quotient by geo is what I mean. Like so Q is just the quotient with respect to this diagonal action, and that's going to turn out to be a free action. I mean, I didn't prove that it's a free action, but it is. I was thinking of torsor, of a G torsor meaning a free quotient, basically, because then all the fibers will just be GO.
Okay.
That.
Sure.
Cool. So
it's already free on the G of K factor, right?
Yeah, that's a good point. Yeah, it's already free on the G of K factor. So yeah, it's actually
sort of like an associated bundle construction, it looks like.
Yeah, basically, yeah, exactly, yeah. And I guess that's also the same notation that we use. So yeah, that makes sense. Good. So maybe the other thing I'm going to note is that we can carry out this construction for as many sheaves as we want, for as many sort of I'll just put like elements of Satake of G as we want. So above we did it for 2, but we could do it for 3, and this will give us associativity. So putting this all together, we get, I think I spelled associativity very wrong. Associativity. So putting this all together, we get that sort of Satake category with convolution is monoidal. So what we want is that symmetric monoidal. And it's going to turn out that in order to prove that symmetric monoidal, we're going to have to think of everything in terms of G bundles. So all that work we did on Wednesday is not going to be completely for nothing. So let's sort of go ahead and start talking about how we're going to prove that this is commutative. And this is actually like the big innovation of this paper too. This is sort of the big idea that Merkovich and Volonin had. So we're going to start by just recalling kind of how we can think of some of these functors in terms of G bundles. So GK of, well, X is a curve. And then GK is going to be things which are F, a G bundle on X, nu, a trivialization on X minus a point, and mu, a trivialization on a formal disk of X. And the affine Grassmannian we can think of as, or is more than we can think of, a G bundle on X, and then nu, a trivialization on X minus a point. So you can think of the quotient disk or throwing away that trivialization on a formal disk. So we want to rewrite the convolution diagram in terms of G bundles. So it might not be super evident that this is exactly the same convolution diagram that we have above. Some of the things might seem a little bit random, but essentially all we're doing here is we're taking sort of the same exact diagram, just converting everything into G bundles. So we have this map P that we had before, and then we have Q down to GR, GX, sort of tilde across GR, GX, and then down to GR, GX. And now we can sort of say what? So all the spaces are sort of Cartesian products of things that we already know, except for this third one, which we're going to have to define right now. And the definition might seem a little bit random, but it's going to be this. So you're going to have two G bundles on X. Then you're going to have a trivialization of the first one on X minus like the point. And then you're going to have sort of an isomorphism between F1 and F on X minus a point. So all I can say is sort of, this is kind of the equivalent of a diagonal action here is going to be to basically have GO. And GO is sort of, you pick a point and then you pick a trivialization on that disk, sort of twisting both mu on the first factor and nu on the second factor. And that's going to get you an eta. So let me sort of spell out what these maps are. So M is not going to be too crazy. So if we have all this information that we just described, we can just send that to, you take F and then you take the composition of these two maps. So, right, so nu1 gave you a trivialization of F1. I should have written that. And then eta gave you an isomorphism between F1 and F on X minus a point. So you compose those two and you get a trivialization of F. Then P is just going to be forgetting something basically. So sort of up here we have an F, a G bundle, a trivialization on X minus a point, and a trivialization on the formal disk in the first factor. And then we have another G bundle plus a trivialization away from the point on the second factor, and we're just going to forget mu1. And then the one which is going to be a little bit hairy is Q. Q is always the one that gives you problems. But Q is going to send sort of this information, which we have from GK cross GR across the affine Grassmannian to F1, F, mu1, eta, where F is obtained by gluing F restricted to X minus the point X and F2 restricted to the formal disk along these maps that you also have. Okay, so that was kind of a lot. And because we sort of defined F to just be F1 on X minus a point, this produces a natural map. A natural map beta. Okay, so so what did we do here? Basically, this was maybe, I mean, definitely it was probably not possible to follow why we're doing each one of these things, but this is basically just transcribing the convolution we have already into G-bundle language. So some of the stuff we kind of already knew how to write, and some of these space and maps turned out to be a little bit hairier. But if you sort of took the time to work through all the details, you would get this convolution diagram out, and it's the exact same one as the one we worked on before, and that's really it. But now Mirkovich and Volonen's sort of big idea in this paper was essentially all the information here is with G-bundles sort of in trivializations all centered at one point. And the idea was, what if we let that point vary, essentially? So in order to sort of take the idea seriously, what we're going to have to do is we're going to have to write one last convolution diagram, which is going to be similar to this one, except the point that everything is focused around is not going to be fixed. That's going to be another parameter that we're going to have to be choosing throughout. And then essentially by sort of moving these points around, we're then F is a G-bundle on X, and nu is a trivialization on X minus all of these points. So that's not too much data, and you'll notice right away that sort of if you look at GR, GX, then sort of over each point. So there's an obvious map down to the curve where you just take the point, and sort of over each point, this is just GRG again. So in general, I'm going to sort of call GR, GX to the n, sort of the endpoint affine Grassmannian. And not only is this true, but sort of if you look at GR, GX2, so in general, we're only really going to care about GR, GX2 and GR, GX1, and you restrict the diagonal, that's just going to be GR, GX, because the 2 points are the same. So it's just a bundle and a trivialization away from that point. So let's just let I be the inclusion of sort of the 1 point affine Grassmannian into the 2 point affine Grassmannian. And now let's think about what's going to happen away from the diagonal. So let's let U equal x2 minus the diagonal. So then it's going to turn out that this 2 point affine Grassmannian is actually just going to be isomorphic to 2 copies of the 1 point affine Grassmannian. So maybe let me explain these maps. But the idea here is basically that if the 2 points are different, then all the data is going to turn out to be local around one of those points. Well, there's going to be data around each of them. But so let's make these maps. So for the map going this way, we're going to take sort of, we have 2 points, we have a G bundle, and then we have a trivialization away from both of those points. And we can just send that to, so we know that we're going to send it to something of this form, but I'll explain how we get each of these guys in a second. So the new I are obtained by gluing the trivial G bundle on X minus Xi with F restricted to X minus Xj, and by Xj I just mean the other point. So actually let me just write this all in terms of 1s and 2s. X minus X2 along new, and you can switch the 1s and 2s to get the other ones. So basically the idea is here, starting with this information on the left, we can just sort of get one affine Grassmannian sort of restricted to each point. And we can recall that the Laszlo-Vogel theorem is telling us that each of these affine Grassmannians on the right, sort of all the information is local to each of the points. So even though it's going to be convenient to sort of define these endpoint affine Grassmannians as sort of having the points be free-flowing, the idea is that the fiber over each of the points is going to have data which is completely local to those 2 points. And actually the whole idea here, this proof, is essentially just that this 2-point affine Grassmannian glues together sort of 2 degenerate situations. So along the diagonal, you have just sort of the affine Grassmannian times the curve. You just have the affine Grassmannian at each point, and the convolution is going to turn out to be exactly the convolution we had before. And then on the complement of the diagonal, the 2 points are different, and all the information is sort of contained in a formal disk around each one, and it's not going to be able to interact. So there's sort of going to be, the data is going to be completely separate. So,
Alberto,
yeah.
can you remind me, what is the statement of the Laszlo-Vogel theorem again?
Yeah, great. That's a good idea. So the Laszlo-Vogel theorem, at least the way sort of I'm saying it right now, is going to tell you that if you have the data of X, a G bundle on a curve X, and then let's say beta, a trivialization on X minus a point. So this is the affine Grassmannian. Then you can restrict it down to F, a G bundle, just on the formal disk around X. So you can restrict the G bundle, and then that will restrict the trivialization. So beta trivialization on the punctured formal disk, and this will turn out to be an equivalence. So it's sort of that thing we're talking about on Wednesday, where if you have a G bundle on the whole curve and a trivialization away from the point, it sort of seems like you have data about the whole curve, but really you just have local data around the point. And this is going to be super relevant to what we're doing here, because essentially now we know that if we take 2 points which are different and we look at this 2-point affine Grassmannian, sort of all the data is going to be local to each of those points. So now we're going to define sort of the global convolution diagram. So this is going to be the last convolution diagram that we draw. And again, there's going to be a similar thing where it might not sort of be necessarily evident sort of why some of the things are defined exactly the way they are. But essentially, it's the way it's defined is so that on the diagonal, you just have the same convolution diagram that we had before. And on U, you sort of have 2 points which don't interact. So I'm just going to go straight to the next page. Cool. So also, I'm sure of writing big X now because it's the global convolution diagram. So I know that can look somewhat similar to a little x, but yeah, this is the global one. And here the middle term is just sort of written like this. And the other one's written like this. And then I guess M maps it down to GRGX2. So notice that the M maps it down to the 2-point affine Grassmannian, not the 1-point affine Grassmannian. And I should, okay, and I should note that this is a diagram over x squared. So what do I mean by that? I mean, at every point, there's sort of a natural forgetful functor that only remembers the 2 points which are involved. And the whole map sort of commutes with this forgetful functor. So at each of these 4 things sort of has 2 specific points chosen, and each arrow just sends those 2 points to each other. So the map doesn't intermingle the fibers. So let's define sort of what these wonky middle terms are, which we haven't defined yet. So grgx cross grgx, which sort of a big tilde, is going to be the following. 2 points, 2 G bundles, 2 trivializations, fi, so a trivialization of each fi on x minus xi, and then an extra trivialization of f1 on the formal disk around x2. So maybe the first observation is going to be that if we let x1 equal x2, then this is just going to be the same thing. Then, well, the fibers over the diagonal are just going to be the same as what we had in the last convolution diagram over a single point. And then let's define this guy to be, again, you pick 2 points, and you have 2 G bundles. And then you have nu1, a trivialization of f1 on x minus x1. And then you have this eta, similarly to we had before, which is a isomorphism between f1 restricted to x minus x2 and f restricted to x minus x2. And for now, I'm just going to say that the maps are similar to in the convolution diagram for a fixed point. Or you can look them up if people want to know. Or I can say them. If people want to know them, I have them written down. I'm happy to say them in the convolution diagram for a fixed point. But basically the idea is, I don't think we're going to gain a ton by writing them, but the maps are sort of the ones that make everything work the way I've been saying. So that along the diagonal, the fiber of every point is just a single point convolution diagram. And along the complement of the diagonal, you sort of have a situation where the 2 points don't interact. Great. Okay. So let's sort
Alberto,
yeah.
Just for my own benefit, can you scroll up to the definition of grg x the m?
Yeah.
Just so I have it in my mind.
No, that's a great
better.
definition to, yeah. Yeah, no, this is a definition which is definitely good to keep in mind. Yeah, so it's, yeah, so it's, you have n points, a G bundle on X, and then a trivialization away from those points. And what we sort of said is that along the diagonal, that's just going to be the same as grx1. So basically you pick a point and then an element, the affine Grassmannian with respect to that point. And along the complement of the diagonal, it's just going to look like 2 copies of grx1. So it's basically going to look like you pick 2 points, then you pick an element, the affine Grassmannian, around each of those points. Yeah, does that, are you sold, Kenny? I mean, is this the definition at the top also?
Yeah. I guess I'm wondering, is there some extra structure that you put on this, or is this literally just like the collection of this data?
Yeah, so, I mean, basically I'm saying it as the collection. I mean, all of these will sort of have some topologies, which no one really talks about, and it would take us kind of very far afield to get into. It's also like the other thing which is sort of going on, which I'm not really going to talk about very much, but maybe it's a good opportunity to mention, is that every single one of these convolution diagrams has similar situation as the first one we're talking about, where P and Q are always torsors over some other functor GO, which in this case looks like you pick a point and then a trivialization of the formal disk around that point. And you need actually that data in order to get like an actual convolution functor, as we sort of talked about. You need to get that Q is a G torsor, a GO torsor for some kind of functor that we're going to call GO, which changes a little bit in the global situation. And you're going to need to keep track of your equivariances throughout. But it's a lot to keep track of, and it's not going to be super important, and it's going to work exactly the same way as in the first convolution diagram, where we actually sort of talked about things more in detail. But yeah, Kenny, what was your original question? I sort of got, you asked if there was additional structure on this. I'm gonna say, like, for our purposes, I would say the best way to think about the additional structure, at least topologically, is kind of what I said. Along the diagonal, it's just gonna look like the affine Grassmannian across the curve. And along the complement of the diagonal, it's just gonna look like the affine Grassmannian across the affine Grassmannian. So that's sort of cheating, because I should have like defined the structure before like talking about like finding its properties. But that's kind of how I would think about it. But in practice, like things like its topology and stuff are not going to be super important. How does that sound? Like if you just think of them as collections, you're going to be good.
Sure.
Okay, great. So now, as we've been sort of saying, we want to think about what this is going to look like over the diagonal and over the complement. So maybe I'll stay on this page. So over the diagonal, the fiber at each point is just a local convolution diagram. So in particular, it's this diagram which I had in a previous page, which we can just go back and look at for at least just to remember which one we're talking about. So over the diagonal, each fiber just looks like this sort of convolution diagram. The first one that we did involving G bundles, where everything is around a fixed point. And then over, however, over U, we have basically that GRG cross tilde GRG restricted to U, and then sort of M sends this to GRG X2 restricted to U, and we know that GRG cross GRG restricted to U, we know that there's an isomorphism here. That's something we talked about already, and it's going to turn out that all of these are sort of the same. So over U, we actually have like a kind of fully degenerate situation where the times tilde is just the same as the usual Cartesian product, and M is an isomorphism, and like nothing super interesting is happening. And in particular, we're just going to kind of note and sort of identify, like from now on, like M sort of box times M tilde restricted to U is just the same, or it's equal. Yeah, we're going to identify these three things, basically. They're all going to be isomorphic. Maybe the sideways equal sign is not the best notation. But yeah, when we restrict to U, sort of box product, tilde, box product, and its push forward are all basically the same thing. So the idea here is we're going to try to glue together this degenerate situation where the convolution diagram doesn't do anything with the diagonal, which is the one that we care about, where the convolution diagram does what we like defined it to do at the very beginning. So for simplicity here, from now on, we're just going to let x equal a1. And the reason why we're going to do this is because thus we can pick a global coordinate and get an isomorphism sort of GRGX, with just the affine Grassmannian sort of cross A1. So generally speaking, sort of the fiber of GX of the 1 point, what we're calling the 1 point affine Grassmannian, its fiber at every point is just the affine Grassmannian. But we want to choose A1 because that'll let us define a global coordinate, and then we can sort of identify all these fibers naturally. And in particular, that'll just sort of let us get a projection map down from the 1 point affine Grassmannian down to the affine Grassmannian. So Mirkovic and Volonin sort of point out, like, you could do this for any curve, being a little bit more clever, but this projection map down is going to make our lives a lot easier. So from now on, X is always going to be A1. Great. So next, sort of like a small bookkeeping thing. So we have this map tau, this is the projection map, and then we're going to let tau circle be tau pullback with a shift by 1, and I circle the I pullback with a shift by -1. Recall that I is the inclusion of the 1 point Grassmannian into the 2 point Grassmannian via the diagonal. And this is the only reason we're doing these shifts is just to preserve perversity. So in general, these I and these T sort of shift the dimension. There's a codimension 1 on each of them, and you need a shift in order to make sure they're going to preserve perversity, but you should just think of them both as pullback. Like, the shift is only to make sure that everything will land in the right dimension. So I don't want to write like lies, but you should just think of them both as pullback. So for the proof, we're going to need sort of 2 statements, which we're going to get from this diagram, and I'm going to write them, and then we're actually not too far from getting, we're kind of past the point where we're just like sort of constructing stuff, and we're finally at the point where we're going to like start kind of proving the statement. So the first fact is that I'll just write it, and then I'll explain why it's fairly reasonable. So also, the one thing that's not ideal is sort of, maybe I should write convolution sub X there, though I don't know if that'll help. But on the right, we have the convolution in the global convolution diagram, and on the left, we have the local convolution diagram. But what's the statement saying here? It's just saying, if we convolve 2 elements to Satake category, and then we pull them back over tau, so we just get sort of their convolution at every point in the diagonal, that's going to get us the same thing as if we just pulled each one separately to the 1 point affine Grassmannian. So we just had A1 or A2 at every point. Then we convolve them globally, and then we just restrict it to the diagonal, because along the diagonal at each point, then we'll just be convolving them. This generally will just follow from some diagram chasing and making sure like you're parsing the definitions correctly, but there's sort of nothing deep going on here. Fact 2 is maybe a little bit deeper, though we're not really going to have the time to like explore the depth too much, but it's that, so let's let J be the inclusion of U into A2, so that's the complement of the diagonal, A2 minus diagonal. And then we're going to have the sort of J intermediate extension of tau 0 of A1, box product tau 0 of A2, restricted to U, is going to be isomorphic to tau 0 of A1, convolved with tau 0 of A2. So what's going on here? So this one's a little bit more substantive, but the idea here is basically that on U, we know that these are the same thing. So on U, this convolution is just defined as the push forward of their box tildes, which we know is the same as just their usual boxes. And then there's sort of this statement that if M, so maybe I'll write, though I don't think going into too much detail would super be helpful, but this follows from the smallness of the map M. So if you have a small map, that basically, I'll just say a small map is one where you have a dense open set where the map has finite fibers and then some dimension conditions on the rest. And if you have a small map, maybe I'll just sort of say if you have a small map, then you can compute the push forward by computing the push forward on that dense open set and then taking the intermediate extension. So in particular here for M, we know that M is an isomorphism on U. So rather than computing sort of, so this we know is just the push forward of sort of this. So rather than computing that push forward, we can just compute the push forward on an open on U, which is just the identity, and then we can take the intermediate extension. So maybe one good way to think about it is sort of like in perverse sheaves, when you have the dense open stratum, it sort of determines a lot of what happens on the lower stratum. Regardless, the idea here is basically that the convolution product of two things on U actually determines their convolution product on the whole thing. And that's going to be super useful for us, right? Because what we want is to understand how the convolution product is going to work on the diagonal in terms of how it's going to work on U. So now that finally lets us get to our theorem that Satake of G is symmetric monoidal. And it's basically going to follow from these two statements. So how is this going to work? So first we're just going to note that if we sort of take the pullback of A under tau, so recall the tau is just the projection map from the 1-point Grassmannian on the affine line to just the affine Grassmannian. So note that the pullback of A for A in the Satake category is just A at every point in A1. So if you pull back on this projection map, sort of all the fibers will just be A. And now having said that, let's sort of kind of go through the computation. So the pullback of the convolution here, this is just a local convolution, by our first fact is going to be this. Then we're going to invoke our second fact. And that's going to get us that this is just going to be the intermediate extension under J of pullback of A1, box product, the pullback of A2, restricted to U. And now, once we just have a box product, we can just switch the factors, because if you just have a box product, it's always isomorphic to just what you get when you switch the factors. So here is where we're finally able. So once we finally managed to write our convolution in terms of only stuff that was happening on U, then is when we're finally able to just switch the factors, and now we can retrace our steps back down fact 2 and fact 1 to just get to A2 tensor A1, and then taking the fiber at any point gives us that A1 convolved with A2 is isomorphic to A2 convolved with A1. Okay, great. So that proves that this category is symmetric monoidal. So maybe I'll just sort of maybe recap a tiny bit what happened in this proof. Basically, we just said if we want to convolve two sheaves, that's the same as pulling them back the affine Grassmannian, pulling them back to the 1-point affine Grassmannian, taking those sheaves, but now on every single point, convolving them globally, and then restricting to the diagonal. Now, once you compute a global convolution, you can compute it only on U, and then that's going to tell you what happens on the diagonal. And what happens on U, well, once we're on U, we're just dealing with a box product of two terms. So we can just switch them and then kind of work our way back down, and then we'll just get the convolution with the two things flipped. So yeah, maybe now is a good point to stop for questions. I should also say that, as I said at the beginning, sort of this was actually the big idea, sort of that Merkovich and Valone contributed in this paper that sort of led them to prove geometric Satake for the first time. This idea of taking this convolution diagram and letting the point vary, and thinking of it as a limit of sort of a situation where the 2 points are different and their data doesn't really interact. All right, so do we have any questions?
Hey, Alberto?
Yeah.
So I spaced out for a bit and forgot like what tau goes from the affine Grassmannian to what? To A1?
Yeah.
Or
yeah, tau goes from, so the idea here is up here, right before that page, we sort of let X just be A1. And the reason why we did that is because, so this 1 point affine Grassmannian, which we talked about, GRG big X, is like you fix a point and then an element the affine Grassmannian with respect to that point. And in general, like all those points, they're sort of isomorphisms. The affine Grassmannian will not be able, we can't identify them. But if you use A1, we can sort of have a global coordinate, and then this 1 point affine Grassmannian will just be the affine Grassmannian cross A1, sort of simply.
I see.
And then we can just do a projection map. So tau is literally just a projection map from GRG big X to just GRG. And we couldn't do that if we took a different curve. Though
and then the I is what? Sorry.
So I is, so we talked about how on the diagonal of the 2 point affine Grassmannian is just the 1 point affine Grassmannian. I is just the inclusion of the 1 point affine Grassmannian onto the 2 point affine Grassmannian on the diagonal.
I see. Okay.
Yeah.
All right, I'm good with the rest. Thanks.
Great. Okay. Any other questions?
Yeah, Alberto, could you say again how you move between the diagonal and U and like what that means?
Yeah. So what's going on here? Yeah. So there's sort of like it can be said like on a formal level or on like a more sort of ideas level. So I'll try saying it on like a more ideas level for now, which is basically just like the idea is this global convolution. So you have this global convolution diagram, which sort of maps down to A2. And on the points in the diagonal, the fiber of the convolution diagram is just the convolution diagram for the affine Grassmannian that we defined at the beginning. On the other points, on U, which is the complement of the affine Grassmannian, the convolution diagram is completely degenerate. And the 2 points don't interact at all. And sort of M is just an isomorphism. And A box product B is the same as A tilde box product B, which is the same, just push forward. So in particular, you can just switch them. So the idea here is basically that we want to figure out what's going to happen on the diagonal by thinking of it as a limit of what's going to happen on U. And on U, we can just switch the 2 factors without causing any problems. Does that help at all, Saad?
Perhaps. Yeah, thanks.
Sure. Yeah, hopefully that made some sense. I mean, definitely this is one of those proofs where like the actual substance of the proof, it's sometimes hard to reconcile with like what's actually going on. But yeah, any other questions?
Alberto, you said that M is an isomorphism away from the diagonal?
Yeah, M is an isomorphism away from the diagonal. Yeah.
Can you remind me, how is M defined again in terms of these bundles and stuff like that?
Yeah, no, that's completely fair. Let's find out where that happened. So M, well, yeah, so the idea is basically, so M, so the thing that M is mapping into is the 2 point affine Grassmannian, so a bundle and trivialization away from 2 points. And the term right before it sort of trivializes one of the bundles away from one of the points, and then sort of identifies it with the other one away from the second point. So if you just compose these two things, you get a trivialization of the second one away from the union of the 2 points. That's kind of how M is defined, like formally. Yeah. Like, well, generally speaking, so whether we're dealing with any of these convolution diagrams, you should always think of M as a kind of like product of the 2 factors, in a sense. So in terms of G bundles, that kind of works out to be a composition. Cool. Okay. Anything else?
Yeah.
Like you have another question, Kenny?
No. Well, it's the fact that I am thinking about like multiplication in some sense that makes this sound kind of strange to me, right? Because I mean, like typically you multiply things, you have this multiplication map that's not an isomorphism in any way, but
Yeah, no, that's a very fair point. So the reason, yeah, that should be weird, right? That's definitely not going to be true for like the convolution diagram for like the affine Grassmannian that we started with.
Right.
And the reason why that's true is basically, again, because sort of all the data is going to be local. So when you compose this sort of trivialization away from one point with an isomorphism away from the other point, sort of like at each of the points, it's only like the sort of one of the trivializations that's doing any work. Maybe that's a bad explanation, but both of like all of that work is sort of, it's not going to interact. It's going to make it all into the image of M.
No, that makes sense.
Okay, cool. I'm glad that made sense.
Maybe I was also thinking about that same question. I feel like maybe the analogy is like the difference between R cross R multiplying down to R is the real numbers here, versus like R tensor R multiplying, and like the cross is the top term in that big span correspondence diagram. Whereas we've taken that balance product, and I feel like that's playing the role of like R tensor R.
Oh, okay, I see.
Is that?
Yeah.
Yeah, I mean, that definitely
reasonable?
seems like a good analogy. Yeah, that definitely seems like
Okay,
a very
cool.
helpful analogy. Yeah.
Yeah.
Yeah. Yeah, Aaron, maybe here's a maybe heuristics that you might like, which is that like what we have this like what we have shown is that we have this cross like this girl thing, and like you can generalize it so it has like a fact like a it has a a chiral factorization algebra structure over this curve, and because of that, and what you're doing is you're just colliding points together in GER G, so that gives you a E2 structure, a chiral E2 structure. And you know that the spherical Hecke, which is GO mod GER G, you also have a E1 structure coming from algebra. And we prove that they're compatible, which means that you can just add E1 to E2, so you get an E3 structure. Like you should get an E3 structure, and as you know, E3 is symmetrically normal. And that's kind of where this theorem is coming from.
Just as a very quick question, is the true thing E3 or is the true thing E infinity?
It's it's not E infinity because like this is not a derived equivalence. So if you go outside the proper sheaf, you're not like it's definitely E infinity. I don't know what it is, but it's not E infinity. It might not. I think it's just E1. I'm not too sure. But this is E3. Okay, then yeah, Sarah says E3, so therefore they're E3.
Therefore it's E3. Proof by Surya. Thanks, Surya.
Yeah.
Cool. Okay. Cool. Wait, what? Was there something else?
Just for the original convolution.
Like the very first one?
Yeah, can you think of it as like stacking raviolis? I guess I'm make sure you can draw. Like wait.
Yeah, that's a very fair question.
Basically,
so
the first diagram you draw is a diagram of these Grassmannians, which are already Magi spaces of G bundles, but do these come from a diagram of actual disk curves? Like just pulling back G bundles along curves. Not the curve.
Wait, can you say that again, Charlie? So at the beginning you were asking about the raviolis, but then at the end you were.
Oh, like the first thing is GER G cross GER G, so maybe that's G bundles on like 2 raviolis, and then the next one's like something else. I don't know.
Yeah, well, it's not exactly GRG is also not exactly a bundle on a ravioli. That's more like GRG mod GO. I'm gonna for now say the answer is probably yes in some capacity, but I'm not super confident about it.
But you're like studying equivariant things on GRG, so like if you're being
that's a fair point. That's a fair point. Yeah. Yeah. So I know that David is a big fan of saying like that you can think of this as like if you take 2 points, like you can either smash them together like this or smash them together like that. So maybe that somewhat answers your question. Okay, cool. Anything else? Okay, cool, great. So so this next part I might have to be a little bit rushed, but but we also need, so we know that this thing is symmetric monoidal, but we also need to know that cohomology is a symmetric monoidal functor down to vect k. And in particular, that's basically just saying that we want the cohomology of A1 tensored with the cohomology of A2 to be the cohomology of A1 convolved with A2. So how are we going to prove this? Maybe a little bit streamlined, but basically let's let sort of B tilde be like the pullback of A1 box tensor with the pullback of A2, and then let's let B be the push forward of this, and in particular, that's just their convolution in the global diagram. So that's how we define the convolution. It's the push forward of the tilde box product. So this proof actually comes down just to sort of looking at fibers of B. So GR sort of X A2, where B lives, naturally has a map down to A2. This is the projection map that we've sort of been keeping track of so far. And we have that the fibers over the diagonal look like A1 convolved with A2 locally, whereas the fibers over U look like the box product. So we want to identify these two fibers. And how are we going to do this? Well, it's going to turn out, I was going to prove this just sort of to be super clear, but you can prove it using base change, that basically the cohomology on sort of the pullback of a point of B restricted to that point is just going to be, you take the push forward of B and you take the fiber at that point. So so maybe for people that aren't familiar with this statement, it can sort of be an exercise in base change. But if you want to know what the cohomology of the restriction of a sheaf to a fiber is, that's just the fiber of the push forward sheaf. And in particular, so now these fibers are exactly the things that we wanted to take cohomology of, right? So if we take the fiber over a point in the diagonal, then we'll just get the cohomology of the convolution. And if we take the fiber over a point that's not in the diagonal, then we're going to get the cohomology of the box product. So to be exact, I should write, we'll get the cohomology of the box product, which is just going to be the tensor of the cohomologies. So all we need to do is identify these fibers, and that's going to follow from the fact that this push forward sheaf is actually locally constant. So maybe that's a thing which I'm not going to prove. I also don't think that's like the most substantive part. It essentially follows from the fact that all these maps which are involved are locally trivial fibrations, stratum-wise to be exact. But either way, this push forward sheaf does turn out to be locally constant, and that lets you identify all the fibers. And then the fibers on the diagonal are just the cohomology of the convolution, whereas the fibers away from the diagonal are the tensor product of the convolution of the tensor product of the cohomology of each of the sheaves separately. So that actually gets you that this is a symmetric monoidal that this is a symmetric monoidal map. That cohomology is a symmetric monoidal functor from the Satake category to vect k. And finally, it's actually going to factor even more. So this I was never even planning to talk about, like to prove in any detail, because it's just sort of going through the last proof, except keeping track of all the weight functors and stuff. But cohomology actually factors as a symmetric monoidal functor from the Satake category to vect graded by co-weights. So we talked about how we get that map, and that map is going to be symmetric monoidal. I don't think that's super surprising once we get the cohomology is, but this will also be symmetric monoidal. So that actually means at this point, we're basically done with the Tanaka conditions. So that's pretty exciting. And we are on to the last step, which is very short, which is the identification of the dual group. So by Tanaka, let me make sure I spelled Tanaka right. By Tanaka, the Satake category is isomorphic to rep of G tilde for some group scheme G tilde. And not only is it isomorphic, but you sort of have the diagram where they both commute with the forgetful functor down to vect k. So we want to be able to show that this G tilde is actually going to be our dual group. So sort of step one of that process is going to be recovering data about G tilde from its category of representations. So there's a few properties of a group which can be recovered from its category of representations. So one which we talked about is that we know the group is reductive if its category of representation is semi-simple. Another example is that a group is algebraic if its category of representations can actually be generated by a single element under direct sum, tensor product dual, and subquotients. So there's a few of these things, and if people are interested, they're all in section 2 of Bowman-Reich. They do a good job actually covering Tanaka stuff, which most people just ignore. And I'm going to continue that tradition of ignoring. So I'm just going to sort of tell you guys what we get from this step. So we're going to get that G tilde is a connected algebraic reductive group. So those show the adjectives that we pick up. And with that, we can move on to step 2. Step 2 is finding the maximal torus. And finding the maximal torus is huge because it'll tell us about the weights, right? So how are we going to find the maximal torus? Well, we're going to do it by this sort of like Tanaka. I'm just going to call it Tanaka 2 theorem because it's sort of in the spirit of Tanaka stuff, which is that if G and H are affine group schemes and you have a functor from rep G to rep H, which is compatible with tensor product, forgetful functor, and just generally outright, etc., because it's just everything that's involved in the Tanaka reconstruction theorem. So like direct sum, for example, you need this to be a map which goes well with everything in Tanaka. Then there exists a unique map from F from H to G such that F is actually just a pullback along F. So this kind of gives us a way to, if we have a functor under representations that's nice enough, it gives us a functor on the underlying groups. So in our situation, we know at this point that we have this map from rep G tilde down to vect K graded by co-weights, and we know what that is. That's rep of T dual. So we get a map from T to G tilde. And we can sort of figure out that this is a maximal torus by sort of looking at a couple facts about their roots and stuff. In particular, sort of the fact that this map from rep G tilde to rep T dual is surjective will actually give you that this is an embedding, or not. It's not surjective, but it'll map onto every co-weight. That'll give you that this is an embedding, and the fact that they have the same, their co-weight lattices have the same rank will give you that it's a maximal torus as opposed to just a torus. But the main idea is just we use this Tanaka theorem, and then we get that T dual is a maximal torus of G tilde. So that's huge because that's going to tell us that the weight and co-weight lattices of G dual are the same as those of G tilde, are the same as those of G dual, right? Because they have the same maximal torus. And the maximal torus is the only thing that's involved in defining weights and co-weights. And finally, step 3, the last step is sort of actually finding the roots themselves. So how are we going to do this? Sort of, we're just going to look at the IC sheaves. So, so it turns out this is something that in an ideal world I would have liked to prove yesterday, but it's not too hard to see that, or I mean, it's not too easy to just see, but it's not too hard to prove that sort of the muth weight functor of the cased IC sheaf just turns out to be the vector space generated by irreducible components of S mu intersect GR lambda. And this tells us, so we talked yesterday about how the places where those intersect are exactly where mu is a weight of the highest weight rep of G dual, where lambda is the highest weight. So this tells us that IC lambda corresponds to the highest weight rep to the highest weight rep of G dual with highest weight. That was not the most efficient way of saying that, but with highest weight lambda, and that it has the same weights. So this is huge because here we're learning that the reps of G, the simple representations of G tilde and the simple representation of G dual have the same weights. So we already knew that they had the same weight lattice, but now we know that their representations have the same weight. And actually, sort of, it turns out, sort of knowing the weights of all the reps, of all the irreps, I should say, is enough to get the roots. And what's one way we could do this? So there's actually a bunch of ways you could do this, and it's kind of fun. But for example, pick the highest weight rep corresponding to some lambda with lambda dominant, and then look at the monoid, sort of mu. Mu is a weight, but mu such that lambda plus mu not a weight of that highest weight rep. So then this is going to be, what's this going to be? Well, it's going to be precisely the positive roots and like their end span. It's going to be precisely the end span. So non-negative positive integers, the end span of the positive roots. And then we can find generators of this monoid. And the generators are just going to be the simple roots. And the simple roots are definitely going to be enough to give us the root data. And that's it. With that, we'll have the theorem. Actually knowing sort of the weights of all the reps is also enough to know the Vile group just by looking at their symmetries. So, so if you wanted all the roots, you could just Vile group. Maybe I'll just write. So to get all roots, just apply the Vile group to the simple roots. So the Vile group permutes choice of simple roots and gets all the roots like that. And you can find the Vile group just by looking at the symmetries of, I think you can pick any highest weight rep as long as lambda is dominant. And you can look at its symmetries and you get the Vile group. So that would be it. That would be a sort of completed proof of geometric Satake, except for all the parts I left out. So yeah, are there any questions? Thanks. Yeah, thanks.
Hey, Alberto.
Hey.
Can I just ask, I feel like I've already forgotten parts of the proof that we did a few days ago.
Yeah,
Can you run down like very quickly what the sequence steps is again that got us to today?
Yeah, no, that's very fair. So yeah, so basically, so the rough sketch is we wanted to show that this satisfies Tanaka formalism, and then we find it's reps of some group, G tilde, and then that group turns out to be reductive, and then we find its root data. We did that in like the last 10 minutes. So how do we show that it satisfies Tanaka formalism? So a big thing is we need to have a fiber functor. So a map down to vector spaces, which turns out to be the forgetful functor from reps down to vector spaces. In this case, that's going to be cohomology. So sort of all the steps really corresponded to sort of trying to prove properties of cohomology, which we need to show it's a fiber functor. So in particular, exactness, faithfulness, and the fact that it's symmetric monoidal. So in order to show exactness, we basically had to decompose it into these weight functors. And that's what we were doing yesterday. And that took a lot of work in terms of looking at, we had these two stratifications, and we had to think about how they intersected, and the weight functors themselves were basically cohomology restricted to these S mu sets. So it sort of involved the definition of them. But after doing a lot of work, we got that each of the weight functors was exact. And that told us the cohomology was exact, showing that faith was not very hard. Today we did the symmetric monoidal part. So that involved giving it a convolution structure. We could just give it a convolution structure, sort of, there's kind of a standard package. Saad told it to us too, when you just have like a group and a subgroup and you have like perverse equivariant sheaves on it. But that just gave us a convolution. It did not tell us that that convolution was symmetric monoidal. To do that, we had to interpret everything in terms of these sort of G bundles and think of the point as moving around and stuff like that. Does that sort of sketch help, Kenny?
Yeah, thanks.
Yeah, there's definitely a lot of stuff that happened. Cool. What other questions do we have?
Surya has one in the chat. He says, is there an example calculation you can show us how to do, like involving some ICs for PGL2, decomposing into the simples?
Okay. So yeah, I'm gonna probably say I don't feel super confident in my ability to do that on the spot, but I will say it's like not super hard. So I could answer that question just by cheating and sort of using the fact that I know what the weights of the IC sheaves are. So like, for example, if you took the I sheet, so for PGL2, like the weights or the co-weights are just isomorphic to Z. And like, if you have the representation with highest weight N, then its weights are just like N through N minus 1. And there's sort of a, like you can calculate how to get like what weights appear in the tensor product of two representations. But like that wouldn't really be a very good answer to your question, because I think the idea was to do it in terms of the actual IC sheaves. Yeah, I mean, it's in like Pramod's book. He does some work showing how he does a couple like showing convolving of IC sheaves, but I don't feel like I would do a great job just doing it on the spot. Yeah, sorry.
Hey, Alberto, so is the entire root datum just given to you by the torus, like the co-roots? Are they recovered? Is that theorem just using that torus and no more kind of the group?
Yes, that's a fair question. So yeah, I mean, if you have like the simple roots and you have the root and the co-root lattices, I think it should be true that like you should be able to identify the corresponding simple co-root. I mean, yeah, that will be true. And yeah, that'll be enough.
I have a question that's probably kind of vague, but hopefully
Sure. Sounds good.
So we showed that the automorphism group of the cohomology functor is the Langlands dual group, right?
I guess, yeah, we technically did. I mean, we haven't even said that out loud, but yeah, whenever, yeah, I mean, because you can identify sort of the dual group in Tanaka by just looking at automorphism of the fiber functor. So yeah, I guess we did do that.
So that means the Langlands dual group literally acts on the sheaf cohomology of these.
Yeah, I guess it does. I mean, I'm just noticing this for the first time too, so I don't know how great an answer I'll have, but that checks out. Yeah.
So is there any like does the Langlands dual group? Do you think there's any way you could say like why these do the sheaves themselves have an action of the Langlands dual group? Like,
yeah.
I don't know. It just seems kind of magic that we later just found that this group acts on the cohomologies. But I guess you think it acts on the sheaves themselves?
Yeah, I mean, that's a good question. I don't know if, yeah, I really don't know. I don't know if anyone else has like a better answer than that, but I think it's like a great question.
Thanks.
Yeah, I guess I have a sort of motivational question. So you said the real kind of crux of, or the original thing in Mirkovich-Volonin is that they decided to do like a many point version of this Einstein-Grassmannian construction.
Yeah.
Or view it as like a moduli space of bundles. So are you saying like people beforehand had sort of realized that the Einstein-Grassmannian, you could like express it as these bundles plus a trivialization away from a point or on a formal disk or something, and that they were just like, dang, if only we could package this together as something over a curve. And Mirkovich-Volonin came along and said, well, look, I can do exactly that. Or was it like, how much did they do?
Yeah, I mean, that's a fair question. Honestly, I'm not really familiar with the history. So I know that they were the first people to sort of, or I believe that in their paper, it was the first time that they sort of interpreted the convolution product as like, they call the fusion product of G bundles, which is kind of like what we've defined. I don't know if like people had already like thought about the affine-Grassmannian as a moduli space of G bundles before them in any capacity. My sense is like, I mean, probably, but actually like over time, like that perspective, I feel like is only becoming like more prominent. Like even in their paper, it's like, it's only like really used in that section where it's necessary. And like now in Zinwenzu's paper, like, it's like, that's just like the definition they use and like how they talk about it the whole time.
I see. Another question, do you think, I mean, like a priori, why did people think that this category of representations is related at all to Perverse sheaves on the Einstein-Grassmannian? Like,
yeah, so that's a good question.
Like, is there a sort of canonical example that people sort of stumbled upon, and then they were like, oh, this is some real shit, and tried
Yeah.
really hard to generalize it. Like,
Yeah, so I sort of like tried roughly to motivate that, and like maybe the first like 15 minutes the first day, which was a really long time ago at this point. But the idea was basically that like they saw pretty early on that these GK double cosets of GO, like just the double cosets as sets, were in correspondence with dominant co-weights, and like dominant co-weights are in correspondence with reps, like highest like irreducible reps of the dual group. So then like it became a question of trying to upgrade that to a categorical statement. And so in terms of just like sheaves, so sort of equivariant perverse sheaves were like the right thing for the IC sheaves to just be in correspondence with like the strata, which were just double cosets. And then sort of, so just at a level of abelian categories, it's actually like not very hard to prove if you're willing to take some statements for granted about like the geometry of GK. What was like hard was to show that you actually have like a tensor isomorphism. So yeah, the statement just sort of without the tensor part, I think was known for a long time before Merkowitz and Bologna's paper.
okay, cool.
Yeah, also, I just saw Tom said in the chat, which is probably worth saying that, yeah, there was a Satake theorem in number theory for a while before that, which I don't really know anything about, but I imagine that was a very relevant part of the motivation.
Like, yeah, I mean, part of it is that you can identify, like, categorification. This is the categorified version of the Satake theorem, which says, basically, I think functions on the affine Grassmannian, but now K is QP and O is ZP. And the functions there can be identified with a Grothendieck group of rep G check. And like that is sort of used to get some kind of like preliminary connection between certain representations on one side. Like it is the data by which one matches the representations on both sides. And by the way, my rep G maybe should have been rep G check, or like there should be a G check. But like the point is that this also stemmed out of Langland's duality first, like arithmetic Langland's duality. And there was like, oh, well, we can obviously also do it for function fields, right? But for the purposes of geometric Langlands, it tends to be like, oh no, we don't want statements about functions. We want statements about categories. Like, for example, well, let me not get into it right now. But the point is like that this is a categorification of a statement that you could have technically, like if you knew all of arithmetic Langlands, you just would be like, ah, yes, I know I'm categorifying this statement. What is the natural categorification? And then,
So you said it originally, like instead of power series and Laurent series, you plugged in QP and then a string of integers.
maybe I want to actually say like a finite field adjoin X. I'm not actually 100% sure. I just know that like one of the big motivations is like one of the big places you could expect this to be true is a statement in arithmetic Langlands, which is a decategorified version. Actually, yeah, let me not say. Well, what else do you want to ask?
Well, I'm just wondering if it's like there's some function field analogy here. I know there's like that seems to be I've just heard this, like that there's even an NLab entry about it, like that there's things in number fields sometimes correspond to things in function fields in theory. And I mean, in the theory of the two of them.
A lot of times, so maybe this is one way that I see what you just said, and I don't know if it's literally the same thing, but like, I think technically if you're doing arithmetic Langlands, you never needed it to be an algebraic number field, you just needed it to be a global field. But it turns out that it's harder to work with algebraic number fields, and correspondingly, it gives you more data. And the reason for that is that there is a place, or like a place you could theoretically complete an algebraic number field is like the Archimedean place, the place whose completion yields reals or complex numbers, whereas global function fields for curves don't have this. I know that is and then so like a lot of the statements that you could say for arithmetic Langlands oftentimes can be proven actually a bit more easily for the function field case. This like I think there's something like someone named Laforgue in 2000 just like full stop proved the Langlands conjecture for all group, or like I think either for all groups or GL, and I think for all groups for function fields. But now interpret function fields as like, you know, the ring of functions for an algebraic curve, and now bump up FQ to C. And this is where the categorification comes in. So that's sort of, I'm not sure if I answered your question because I think I forgot your specific question.
I didn't really have a question. I just wanted to kind of explore random thoughts that popped into my head.
Alberto, I have a question. I might be sniping you because this is like a big thing for characteristic P Satake, but here's my question. You could forget down to just Iwahori equivariant sheaves on the affine Grassmannian, and we're in characteristic 0. Does that have a correspondence to a subcategory or something, or not even necessarily a subcategory of something, but in function fields? I mean, in rep G check?
So I think you probably know this much, but like if you forget down to just Iwahori equivariant sheaves, you just get like if you take sort of Iwahori GO double cosets, you just get not dominant cohorts but all cohorts.
Yes.
But as far as I know, I don't know if you get anything at the level of G check. Yeah, like your reps of G check. I mean, do you know to any extent if it?
No, I mean, I know. So there's this fancy thing called the Finkelberg-Merkovich conjecture in characteristic P that I know about, which is why. But like, that seems like I should know the characteristic 0 thing first. But the Finkelberg-Merkovich conjecture says if you forget down to Iwahori invariance, what you get on the rep G check side is the Frobenius twist.
Oh wow, that's intense.
I know it's like an awesome theorem. But the Frobenius twist obviously doesn't exist for characteristic 0, and I don't know what it should be, and so I'm soliciting all of my friends for answers before I message David about it.
Yeah, that's a good question. I mean, if we're just kind of like saying random things, like the only thing I could sort of guess is like if you're indexed by just like all co-weights instead of dominant ones, maybe it has something to do with like not just finite dimensional reps, but like all kinds of reps of like the Lie algebra or something like that. Like maybe, but that's just purely 100% just trying to imagine what things could be labeled by all kinds of co-weights.
That makes sense, or at least sounds mildly plausible.
Yeah. Yeah. Cool.
Thanks for this course. This was great.
Yeah, it was good. No, thanks for coming. I mean, should we maybe end the recording at some point?
Yeah.